In this video tutorial, we're going to learn how to program a 7-segment display. We've done a previous video where we used Verilog bitwise operators to program it. We used Boolean expressions, but now we're going to see how to use Verilog case statements and always blocks to do that. So we're coming back on revisiting the 7-segment display exercise. We're going to program this to an Altera board, and we said our 7-segment display looks like this. It has 7 separate LED segments that we can light up. The segments are all numbered 0 through 6. What we did in the previous exercise is we determined what sets of LEDs we had to light up for certain numbers. For example, if we want to show the digit 0, we're going to light all the segments except 6. Right, so we'll have 0, 1, 2, 3, 4, and 5 in our set lit up for the number 0. And we determined those, and we created then these sets of segment numbers that we wanted to light up. Similarly, if we want to show the number 1, we're going to light segment 1 and segment 2. So we came up with this set. So we came up with our sets, right? And we're showing the digits 0 through 9 and then A through F because we're showing hexadecimal. Remember, we need 4 bits of input to show, we need 4 bits to show F. And so we have 16 unique combinations here on our binary input truth table. Right, we came up with these 7 segment sets. I'm getting a little ahead of myself with the truth table. We translated those then sets into 0s and 1s. So on the Altera board, it's an active low to turn the segment on. In other words, a 0 will turn an LED on, and the 7-segment display 1 will turn it off. So going back to our set for the number 0, remember we want to turn on every segment except 6. So we developed then this binary encoding. 6 then was a 1, so that's off. So for the symbol 0, 6 is off, and all the other segments are 0s, meaning they're on. Same way for the symbol 1, we said we wanted to turn on segments 1 and 2, so they are both 0s, and all of the other segments are 1s. So we completed this in a previous exercise. We came up then with this hex encoding. In other words, we took these binary digits and turn them to hexadecimal values, right? So we need 4 bits to do that. We start from the least significant bit, which is S0, and these 4 bits came up with the encoding, hex encoding of 0, right? These 3 bits then with a hex encoding of 4. That's where we got the 4-0. Similarly here, we get a 7-9. This is the binary pattern for 9 here, and here, these bits are the binary pattern for 7. So we came up with this hex encoding in the previous exercise. We didn't use it, but we are going to use it now to write Verilog. So we'll want to use these numbers then to create that pattern to light up our LED. Right, I'm going to minimize this. I'm going to bring up the previous Quartus project we were using as a reminder. So when we completed that exercise before, we actually then came up with a set of Boolean expressions. So after we did this in the hex encoding, last time we copied all of these segments over to a truth table. We said each segment was an output. So our inputs were labeled A, B, C, and D, and there are 16 unique binary patterns here. Our outputs then were each of these individual segments, and then we had to come up with, sorry, didn't want to highlight them all. Yeah, looks like it's highlighting them all. For S6, we mapped the 0s and 1s to a K-map, right, and came up with an expression. So here's S6. I'm just showing the 1s here, not the 0s. Solved for the 1s and came up with this Boolean expression. We did the same thing for S5, S4, S3, S2, and S1. Came up with these Boolean expressions. Once we did that, we put them into Verilog, right, into this module, where we then programmed it to an Altera board to see the patterns on the 7-segment display. Well, as I said, we want to move away from the Verilog bitwise operators and start using always blocks. We're going to rewrite this module to do that. Right. Let me make a new Verilog file. All right. So we're still going to implement the same behavior, just in a different way. I'm going to copy these comments here. All right. So I won't call this hex to 7-segment bitwise. Maybe I'll call this case for case statements. All right, same behavior. So we're going to start with the keyword module. X7 seg, calling it case, because I'm going to use case statements. Right now, my input, right, over our truth table, we were calling this A, B, C, and D. All right, and then we had our output wire of our 7 segments. Well, I actually don't want to call this A, B, C, and D anymore. I'd rather just refer to this as a 4-bit binary bus. But not to get too far away from what we started with, let's keep this and I'll show you how to make a concatenated signal. So our output was S for segment. All right. I want to make this look as much like the other module as possible. At first, we'll try some new techniques. All right, so our input wire, these are all individual bits. Our output wire, our segment S, then we made 7, 6 down to 0. All right. All right, well, what we want to do now is we want to write an always block. We want to say always at, and then put our sensitivity list. So our circuit is sensitive to changes in our inputs, right? So we're going to put all our outputs in there. Sorry, our inputs. So circuit is sensitive to changes in input signals, right? So we put the input signals in our sensitivity list. Whenever there's a change in any one of these, it will activate this circuit. Right. I'm going to put a begin block and an end, begin and end, right? So I can put my code inside here. And then I'm going to use something called a case statement. Well, what I want to evaluate are each one of the individual binary cases. I want to evaluate then, right, when my input is 0, 0, 0, right? And what I'm going to do is I want to look at the case when I have a 4-bit binary input of 0, 0, 0. Well, I need to be able to evaluate A, B, C, and D in a way to represent a 4-bit bus. So I could use perhaps concatenation here and say A, B, C, D. So the left and right curly braces say to treat that as a concatenated signal. Take those single individual bits and treat them as a 4-bit bus, where A is the most significant, B is the least significant. And so I use the syntax of the keyword case. Right? Based on its value then, I want to come down here. When the input, so when ABCD matches this pattern 4-bit binary 0, 0, 0, I want my output then to be, I could type the pattern that we had in the table, which would be a 7-bit binary. We turned off segment 6 and we turned on all the others. Right. We could type out the binary for that, which is the same as our hex 40, that encoding. Right. So that gets a little bit tedious to type, right? Typing out those binary patterns over and over again. So instead of typing the binary, let's go ahead and type in our hexadecimal value that we encoded. Let's change this then. Now, I still need a 7-bit signal. Remember, our output is 7 bits, so that's what the 7 says. 7 here is the size, the apostrophe is the syntax. H says, I'm going to write now the number in hex. So I'm going to write a 40. So I want my output pattern, that will still be then binary 1, 0, 0, 0, 0, 0. All right, that's our binary pattern for S6 through S7. As a matter of fact, I could put in a comment here. It says, what's S6, S5, S4, S3, S2, S1, S0. it looks like this. So all we're doing really is typing that pattern. In other words, what we're going to do in the case statement here is we're going to type what looks like the truth table, right? These are our inputs, A, B, C, and D. A, B, C, D. That's the pattern that forms. And then there's the pattern our output forms. So we have the keyword case. We want to evaluate this as a 4-bit signal. We don't want to evaluate these individually, so we had to do the concatenation then to say treat these as a 4-bit binary signal, form a number out of those 4 separate bits. And so what we do now is we say, okay, our input is a size 4, right? I don't have to type in binary after this. I could type in other bases, but let me just type it binary so it'll look like the truth table. Now, if I say S is equal to a 7-bit hexadecimal, well, our other encoding on our next one, if I bring this back up, right, here's our hex encoding here. To minimize this down a little bit. Yep. I'm trying to leave 2 things on the screen at once. Right, notice our next one is a 7-9. We go back to the table, then we say we want 7 bits in our output. The base we're typing here is hex, and we're going to type a 7-9. Well, that's the same thing as a binary, right? 1, 1, 1, 1, 0, 0, 1, 1. Remember, we're trying to represent the digit 1, and we said in order to do that, we only turn on segments S2, S1, and turn all the others off, right? All right, now, before I go any further, there's one thing we need to bring up. Here I am using S, right? Which is a wire type. Any signal that's on the left-hand side of an assignment statement. So this is the assignment operator, the equal sign. So this signal is on the left-hand side. Well, this signal type must be a reg type to be on the left-hand side. So inside an always block, the signal on the left-hand side of the assignment operator. So this signal must be a reg type. Right. It needs to be the same size as S. So I could theoretically type reg 6 down to 0, and I could say make S both a reg and a wire. Quartus does not like that. It will generate a compilation error. So I tend to name my reg signals the same thing, a similar name. So if my output signal is S, my reg signal I'll just name RS. Meaning in here, all of these need to be RSs. Right. And let's go ahead and finish then our Verilog, right? So when our input is a 2, there's our binary pattern. RS for our output of 2 should be a size 7, hexadecimal, and the number we're coming up with next is a 2-4. So a 2-4, right? Which is binary for 0, 1, 0, 0, 1, 0, 0. And similarly, right, when my input is 3, RS, I want to assign to RS 7 bits. So this constant, this integer constant I'm typing should be 7 bits. And then, was that a hex 30? That was a hex 30. So 301912. Right, 4-bit. Okay. 10. So 010 RS equals 7-bit. You said that's a hex 12. Right. 4-bit binary 0110. RS is going to be a 7-bit hex, and our encoding then is 2780. So 2. 78. This is 0 because we're turning on all segments, right? 0, 0. 4-bit binary 1, 0, 1. So the number 9, what are we turning on? 7-bit hex. Number 9. Right, we're turning it. So 180803. 1818. 08 is the pattern for 10, or A, right? We want to see an A. Binary for 11, which we want to see. We're going to see a small case B. Did I say that was 03? 03, and then a 46 and a 21. I said 46, and then 13. Let's see, hex 21. Binary. Here we go with 14. We want to assign to the red signal, RS. And then 060E. And left out the H there. All right. My last input, RS, equal to a 7-bit 0E. All right. And then we have to have an end case statement. So all one word. So the syntax for case is inside parentheses. You want to put the signal you want to evaluate. We're evaluating the 4-bit signal, right? We made that concatenated signal with the curly brace operators, where the left-hand side is our most significant bit, the right-hand side is the least significant bit. And then as you can see, what we've done in effect is we have just typed a truth table in here. We've typed all 16 unique binary combinations. We've said what we want the output to be. And when we use Verilog in this manner, we're just really modeling the behavior of the circuit, right? We didn't have to come up with any sort of minimized equations to do this. So this is why Verilog is a fast prototyping tool. Right now, what we want to do is we want to save this. So remember, we have to save this with something of the same name. All right, so I'm going to say, I'm copying that, Control S, right? I want to make sure I save this in my project file, not the output file. And so hex 7 segment case. Right. Now, I'm going to remove the bitwise operator file from the project. Now, here are the changes we need to make to the hardware level. The hardware level, notice then our signals, our inputs were still the same names, outputs were the same name. All I have to do at the hardware level is I change the name of my module to case. All right, so on the board in previous exercise, we said we wanted to use the 4 switches, so 3 down to 0, to represent then our binary inputs. This is the hardware name for the DE2 board, SW, right? The hardware name for the output of the 7-segment display is hex 0. It has 7 segments. To instantiate the module, we use the module name. In this case, hex 7-segment case. I created a unique instance number. To those signals, we need to wire the hardware here, this hardware level. So switch 3 is getting wired to A, dot A, switch 3. Right, switch 2 is getting wired to B, switch 1 to C, switch 0 to D, and then our 7-segment output will get wired to the hex display. Right, so the hardware level is my top level in here. In this particular project, right, I'm working on a DE2 board. I already have my device set up. I've already imported my pins. I'm just going to run the compilation now. See if I can get this ready to program to the board. And I saw a warning message going by that I didn't like. It looks like S at hex 7-segment case has no driver. Yes, I did not finish. I got so busy talking, I forgot to tell you the last step. So talking and not thinking, not a good thing. So notice this warning, output S at hex 7-segment has no driver. A driver meaning there's nothing then to drive the output signal here. The reason is did I make any assignments to S? No, I did not. So the last step we have to do is we have to assign the reg signal to the hardware signal S. So we say, assign the reg signal to the hardware signal. This assignment statement with the keyword assign is known as a continuous assignment statement. The signal on the left-hand side in a continuous assignment statement must be a reg type. So signal S on left-hand side of continuous assignment statement must be a wire type. So this with the keyword assign is continuous assignment. This signal has to be a wire type. Signal on the right-hand side can be any type or any expression. Right? The difference here, then inside the always block, this signal RS on the left-hand side of the assignment statement must be a reg type. I'll put a comment here that says, in an always block, the signal on the left-hand side of the assignment operator equals must be a reg type. All right. To drive the signal S, assign the reg signal to S. Right. So that's why I have to look at those warnings. I'm going to save that. I'm going to rerun that. That warning's not going by. Just waiting for this to finish compilation, and then we will try programming the board. All right, compilation successful. All right, what I'm going to do now, I'm going to start up the video. So all I have is my Altera DE2 board plugged in. Right, you can see that it's just flashing, right? There's nothing in the memory. Remember, if we power, if there's a program in there, if you power it off and then power it back on, since I have it in the run mode, not the program mode, it loses any program that was previously in there. So I'm going to now go to the programming step. So here the programmer, right, it already detected my USB blaster. It's already got my output file in here. I'll just say start. And it says it was 100% successful. All right, let's look at the position of my switches here. All right, I'm going to put everything all, so switch 3 is here, right, 2, 1, 0. All right. So now we see the 0 output on the 7-segment display. So my input binary pattern is 0, 0, 1. There's our 1, 0, 0, 1, 0. There's our 2. There's our 3. 0, 1, 0, 0. There's our 4. Right, 5, 6, 7. Let's see. I go with 8. Oops, sorry, that was 0, 1 followed by 3 zeros. There's 8. There's 9. Right, 1, 0, 1, 0. There's my A. There's my B. All right, 1, 1, 0, 0. There's my C. There's D. There's E, and then there's F. All right. So now we've successfully used case statements to program the board. Stop the video here. We've programmed the board then to show our 7-segment display. All we had to change at the hardware level is the name of the module, because we still, when we wrote this particular module, we still used the same port list A, B, C, D, S, right? But we wrote it with case statements. So we wrote it behaviorally, our first example, with an always block for the 7-segment display. Right, now notice when we ran this, all the other displays were turned on. Maybe I want to add something like an enable signal to this to determine whether I want to just turn the device on or off. Because right now, right, this will just expect the inputs 0 through 15, turn it on. But what if I want to add an enable signal so that I can use the module to turn off other displays at my hardware level, at my top level? At the top level, let's say I wanted to add hex 1 as well. So I'm going to add hex 1 here. And it's 7 segments, so I'll just add that to the list here. All right. Now both of these are enabled. If I want to turn this on, I'm just going to copy that, create another instance of this module, give it a unique instance number, and now my output would go in hex 1. All right, so if I drive it with the switches, I'll just save that. I'll recompile. We'll reprogram this in a minute. If we drive this with the switches, right, we're just going to see the same output on 2 different hex displays. Let's bring up the programmer here. I'm going to reprogram the board. All right. So now, right, I've got all 4 switches at once. We see FF on both. So no matter what we do, we're seeing the same outputs on, right, this 2 different displays. So we just enabled another display then by creating an instance of the module and saying we want to show the same outputs. I could wire different switches to that so that we could show different outputs on there. But what I'd like to do next is I'd like to have a way to just turn an LED or 7-segment display completely off using an enable signal. Right. Now what I'm going to do is I'm going to do a couple other things to change this module as well. We want to get away from writing ABCD. I want to start creating 4-bit buses. What I'm going to do now is I'm going to change this input name to binary value. And now this has to be 4 bits wide. I'm going to name it binary value. Binary value, right, bit 3, that's my A, bit 2 is B, bit 1 is C, bit 0 is D. Right, but since I'm implementing the truth table, I really don't need this ABCD thing anymore. I just want to say always at binary value. And I don't need the concatenated signal in here. Right? Just change this to binary value. And I'm going to save that. Let me do analysis and synthesis quickly. No, I don't want to save the programming tool. All right. So I said I'm going to do that quickly, but did I change my top level? No, and there's where my errors are, right? Because once I made the change to this module, when I said analysis and synthesis, since both files were part of the project, it generated an error over here in my top level. Right, so now to connect to that here, all I need to do here is to change this to binary value. Right. And I can use the name SW. SW refers to a 4-bit signal. Binary value also refers to a 4-bit signal. Right. So it's just going to connect switch 3 then to binary value 3. So let me save that. Let me just, no. I want to stop compilation because of course I'm going to get an error because I did not change this other one. All right, so let's recompile. Now I don't want to save the programmer. All right, and it's giving me a warning because I've still got hex 1 in the port list here and I'm not using it. That's not the best programming idea. So I'm going to stop the compilation. I'll recompile. Our circuit would have worked, but I should follow good programming practice. And this one's not. Yep. And I should pay attention to what I am doing here. So doing examples on the fly for you is not my forte today, is it? one more time. Third time's a charm, we're gonna hope. Okay. All right. So when we see this, right, I'm going to put the switches, I'm going to put those in position 0, 0, 1. This is the old program still on there. Both of the hex displays are on. When it finishes compiling, I'll just go to the programmer. And reprogram. Now that we've reprogrammed, this is back to an 8, so I've got all these 8s on. I'm just seeing the number 1, but my circuit is still working there. All right, now to add our enable signal to this. I'm going to add another signal to the list. So besides binary value, I just call this enable, right? Sometimes I like to call it display on. That's a little more descriptive to me. Do I want the display on or do I want the display off? So I think I'll just go with display on. This is going to be a single bit of input. So input wire display on. I'm going to add some code inside the always block. So right here, inside of this begin, I'm going to add an if statement that says if display on equals 1. I need a begin and an end for my code in here. I'm just going to grab this and indent this. All right, indentation then helps me see what level this goes with. All right, so if display on, so this double equal sign is a relational comparison operator, right? If it equals 1, and I should then make this a size signal. If I don't, it'll make it 32 bits by default. So a 1-bit binary 1. Right? Because this is a 1-bit signal, I want to compare it to a signal of the same size. If display on is a 1, I want you to go through and implement the behavior that we've just seen. Else, if it's a 0, because it can only be a 1 or a 0, so else, then what I want to say then is I want to turn everything off. And a series of 1s in the output would turn everything off. So I'm going to just say else rs is equal to a 7-bit hex 7f, which is then 111 111. Turns all segments off. Now I use an if-else structure. So if true, do these statements. Don't do this when the condition above is true. But when this test condition, this Boolean expression is false, then we come to the else branch and execute this. Right. Now I'm going to save that. Since I added a signal to this right here, then at the hardware level, I also need to make a connection. It doesn't have to be first, but so I call that signal display on. I want to connect to that then. I'm going to connect, let's see, I'm not using switch 4. I'm going to use switch 4 to connect to that and say whether or not I want to turn a display on. Use a switch to do it. I could actually hard code a number, but let's just add another switch to control that. All right. Now, if I change the size of the bus with the switches to 5, I can no longer just use the name SW here because I'd be referring to all 5 of these. So now I have to very specifically say I want to connect to this, which is 3 down to 0, to binary value, and switch 4 and my input. Let me save this. Let's recompile. Okay, let's program. Notice my hex 0 is turned completely off because when I switch 4, right, sorry, my switch 4 is at a 0. If I flip switch 4 on, notice we've got a 0 because 3 down to 0 are zeros. All right, so if I then put, there's a pattern of 5, I've got that on here, but now if I turn switch 4 back to 0, it turns my display off. So I can control, right, with another piece of hardware whether I want that display to be on or off. One more change to our program here. Let's create more instances. Instead of controlling this with a switch, let's just control this with a constant, integer constant. So a 1-bit binary 1 says I want to turn that on. I'm going to put these switches back 3 down to 0. I could leave that syntax there. That's not incorrect. Right. And now let's create another instance. Right. For hex 1. I want to turn hex 1 off. I need to add that back into my port list. I need to give that its own unique instance number so copy paste doesn't get me into trouble. So we should see hex 0 on, hex 1 off. And if we recompile this, all right, I'm going to turn the board off to lose the last program. Don't have to do that. And we're going to wait for it to finish compiling so we can program it. All right. Successful. Here's my programmer. All right, now let me show this. I'm no longer using a switch to control on or off. I said hex 0 should be on because it has a 1 in it, so hex 0 is on. But notice then the 0 that we encoded to that instance, so to this instance right here, the 0 that we encoded said, go ahead and turn that display off. All right, so we then can take control. If I wanted to turn all these others off, I could add that as well here. Right, we can see our switches are still controlling the output on this one. All right, so that was the lesson we wanted to learn today. Is we wanted to learn, first of all, how to use case statements to implement this circuit. We did that. Once we did that and tested it, we also added this enable that I called display on. So if display on was set to 1, right, we got the same behavior out of our circuit. Otherwise, if it was set to off, we just could turn off those other displays that we didn't want to look at. All right, thanks for watching. Hope it worked for you.